All right. So now you guys know MongoDB is working toward transactions, and we put this little video series together to walk through some of the technical implementation of projects leading up to transactions. I'm Ali Cabral. I'm a product manager on the core server. I focus mostly on distributed systems, so replication and sharding. And I have Michael with me, who's the director of engineering for storage. And he's going to introduce himself and walk through what we're going to talk about today.
Thanks, Ali. So my name's Michael Carl. I've been working with databases for over 20 years, and I have a background in transactions and transaction processing. I did a PhD on efficient processing of transactions while making sure that applications get correct results. And I started a company, co-founded a company in 2011 with Keith Bostick in Boston called WiredTiger. In 2014, WiredTiger started working closely with MongoDB and realized that we'd solved some of the problems in the storage engine that MongoDB had in its database. That led, at the end of 2014, to MongoDB acquiring WiredTiger and the WiredTiger team coming across and joining MongoDB. And pretty soon after that, we started having a conversation around transactions because WiredTiger is a transactional storage engine. And so very quickly, the question came up is like, how hard could it be to make the whole of MongoDB transactional if the storage engines are already providing transactions internally?
And how hard did that turn out to be?
Well, so that's really what this talk is about. It turns out that there are still some pretty hard problems to solve, and really that's what we've spent 3 years working on. And so what I'm going to talk about today is some of the ways that we've tied together MongoDB's requirements for transactions with functionality in the storage engine. And really, this all comes together around the idea of timestamps in WiredTiger. So I'm going to explain what they are and some of the things we can do with them. Okay, so the issue is that MongoDB is a distributed system, and the replication layer in MongoDB writes individual operations as they happen into something called the oplog, which is a special collection inside MongoDB.
Short for operation log.
The operation log, exactly. And the order of operations that appears in the oplog is really important for the correctness of the system as a whole. If each node in a replica set doesn't end up with the same operations in the oplog in the same order, then they'll end up with different versions of data, and that's equivalent to the data just being corrupted or lost. So the oplog in MongoDB implies a certain ordering of operations. But traditionally in storage engines, the storage engine itself has its own idea of ordering. So this is called concurrency control, and WiredTiger provides a version of concurrency control called multi-version concurrency control, where as the operations are all happening in parallel, the storage engine gets to decide what order they're recorded in the journal underneath, in the storage engine's idea of the ordering. And the journal is important in terms of what values can be seen, so what values are read by queries, but also what values survive if there's a crash. So if the order in the oplog, as you can see here, 100, 101, 102, is different from the order that the storage engine records, here you can see 102 comes before 101, this can lead, unless we do something else, this can lead to replication not getting correct results.
Right.
So what we've done in WiredTiger is really re-architected from the ground up to allow this ordering that is determined here by MongoDB to be reflected all the way down inside the storage engine.
And before making these changes in WiredTiger, we had to deal with this at the replication layer.
That's right. So we had some fairly complicated code up in MongoDB that was tracking what operations were in flight and controlling how threads could read the oplog. So part of what we've done with timestamps is allowed all of that processing to be pushed down inside the storage layer where it can be handled more efficiently.
Perfect.
And so to give you an idea of what it means to re-architect WiredTiger from the ground up, I want to talk just a little bit about some of the data structures we use to represent data inside WiredTiger. So when you store documents in a collection in MongoDB, there can also be indexes associated with that collection. And all of that data, the documents and the index entries, are stored inside a tree in cache. So this is WiredTiger's kind of primary data structure, is this kind of tree. And inside a tree are keys that allow you to navigate around, And then you find leaf pages here that have keys and values together. And these values might be the BSON for a document, or they might be the index entries that are used to store indexes. And anytime one of those things is updated, so if you change a document or you insert a new document, we create one of these things that WiredTiger calls an update structure. And an update has inside it some information about the transaction, a link to the next update in order, and the data that was changed as part of that update. And when reads come in and they need to figure out what value should be returned, WiredTiger has its own internal logic about following these lists of updates to return the correct one. And this is the basic mechanism of multi-version concurrency control that's been in WiredTiger for a long time. But the change we've made is right here. So we've changed this really fundamental data structure to add a timestamp, or what we're calling a timestamp. And this is a value that the application, in this case MongoDB, can pass in and tell the storage engine what order things should happen in.
So now MongoDB can send this down to the storage layer, and the storage layer will respect that time as something valuable that it should respect.
Exactly right. So MongoDB can do two things. It says the order as the updates happen, and then what it can do is ask to read as of one of these timestamps. So then if you query as of a timestamp, WiredTiger will make sure that you see exactly the values as they were at that time. And this is true even if there are lots of operations going on in parallel and some of these updates arrive in a different order, or they're installed in a different order by WiredTiger than the timestamp order. The timestamp is still used to guarantee correct results.
Great.
So we've really changed, right down at this fundamental level, we've made changes inside the storage engine in support of transactions. And so now I want to move on a little bit to talk about some of the things we can do now that we've got this timestamp mechanism in place. So I mentioned that MongoDB creates an oplog as operations are applied on a primary. And then the oplog is what's used by replication to get that data onto multiple nodes. So each replica set node reads the oplog from the primary and builds up its own local copy of the oplog. And then it has to apply those oplog entries on the secondary in order to bring the collections and indexes up to date. Mm-hmm. And the way this is done is by breaking the oplog into batches. So we take some set of records that are together in the oplog, and we split those records up amongst multiple threads here and apply them in parallel. The reason we do it in multiple threads is that if we do it in just one thread, it can't keep up with all of that work that's going on the primary. So we have these multiple threads here, and we have a clever technique for sharing this work out amongst these threads, so that most of the time, if we have related updates, they go to the same thread and they end up being applied in the same order on the secondary. However, across these updates, they can apply out of order. So you can see here that although the oplogs in the expected order, 100, 101, 102, that the order that the threads do the work is 101, 100, and 102. So there's a different order again to maybe what was in the journal.
And each of these entries in the oplog represents a modification in the database.
Exactly.
An update to your data.
Exactly right, yeah. So they can be a field update or a new document being inserted or various other kinds of updates. And applying them can both change the documents on the secondary, but also change indexes.
Right.
And so there are several things that we can now do now that we're labeling all of these changes with timestamps. One of those is that we can resolve this difference in ordering for queries. So when a query comes in, even though these have been applied out of order, what WiredTiger timestamps allow you to do is come in after the fact and do a query as of timestamp 101, say, and WiredTiger will show you the right things. It'll show you the changes, the update in location 100 and 101, but it won't show you this one here in 102.
So you never see 100 and 102 without 101, right?
Exactly
so you're
right.
always making sure you're seeing a consistent state of the data.
Exactly. And that then solves some problems that have kind of been long-standing issues in terms of the way MongoDB's replication works. So let me talk a little bit about one of those. So I said we split the oplog up into batches, and each batch is applied by multiple threads. And the batch boundaries have typically been identified with locks. So as we're applying this batch here, MongoDB internally is holding a global lock for that period. And what that means is while we're applying these things, reads can't execute on a secondary.
Because it wasn't safe, because you could get an inconsistent view of the data, because the order of the batch application is not guaranteed in any way.
Exactly right. And so what we've guaranteed that reads are correct on secondaries using locks up until now. But what that means is that at these batch boundaries, first of all, the reads have to wait for the batch to complete. But also, if the reads themselves take a long time, then replication itself slows down because it has to wait for these reads to finish on the batch boundary before the next batch can start.
Which could lead to replication lag, among other things.
Absolutely, yeah. And so one of the things we're addressing inside the storage layer and with replication is allowing reads inside this previous batch. So here in batch 1, once it's completed and we've moved on and we're applying things in batch 2 here, all of the changes inside batch 1 have been applied and they have timestamps. So it's now safe to read inside there up to this timestamp of the batch boundary, and correct results will be returned. And that means we're moving towards a world where we can read on secondaries without any locking at all.
Right, but you wouldn't see any changes in the batch until all of the batch is complete.
That's right. So we apply all of batch 1 and wait for all of the threads that are doing that work to complete all of their work before they move on to batch 2. And then the reads can start reading in this range here between the timestamps at the beginning and the end of batch 1.
Perfect.
Now, one of the specific problems that we've had to resolve in this code path relates to indexes. So even though I said we split up the work among threads and we have a clever way of sharing that work out, it can still happen that 2 different threads are working on documents that have the same unique index key if you declare a unique secondary index. And so one of the things we've had to figure out is how to make it safe to read during that batch if there were collisions on a unique secondary index key. And that's involved a change to the format of indexes to support those reads. So there have been various projects in here to make all of this work correctly and provide correct results.
Awesome.
Okay.
I'm personally really excited that we're going to be able to service reads during apply ops on secondaries.
Yeah, likewise. I think
change.
it's going to improve things for our customers, but it's also going to improve some things internally for some of the operations that MongoDB itself does.
Perfect.
So the next thing I want to talk a little bit about, another application of timestamps, is related to replication again, but in this case, what I want to talk about is replication rollback. So to understand this, we need to understand a replication concept, which is the majority commit point. So that's what I'm going to try and explain right now. So as I said, the oplog is built up on the primary as operations complete there, and secondaries read the oplog and make their own copy, and then they apply those operations. But the secondaries are all at different points.
Right.
So you can see this secondary 1 here has applied up to this point of the oplog. Secondary 2 has gone all the way to the end, so it's up to date with the primary. There's no lag. And secondary 3 is right back here. So it's further back than the other 2. And what we care about for the purposes of changes becoming durable across a replica set is what's called the majority commit point. So this is a point where we know that a majority of nodes in the replica set have all got that oplog entry.
And that's important because you know that point will never be rolled back and is safe and secure in a case of election or a node failure.
Exactly right. So once we've reached that point, and I'll show you where it is here. So here you can see secondary 1 has this one. Secondary 2 also has that same oplog entry. And even though secondary 3 doesn't have it, still a majority of nodes are up to this point. So this is our majority commit point in this scenario. And yeah, exactly as you said, that's the point where we know no matter what happens in terms of how you've configured your systems to handle different kinds of failures, any of those failures can happen and no data older than this point will be lost.
Perfect.
Whereas some of these other updates that might have been in flight on the primary but haven't yet been copied over to a secondary, if you pull the power on the server that's running your primary, then you could potentially lose these updates.
Yep.
So the reason this matters is because we can lose that history. So if a primary does go down, so this node on the left here used to be the primary. If it goes down and then comes back up again, in the meantime, typically what's happened is some other node in the system has become the primary of that replica set. And when the old primary, comes back up to rejoin the replica set, it figures out that it has some history here that's no longer part of the new replica set.
So it's no longer a valid history.
Exactly right. So these are those kinds of writes that were accepted locally on the primary, but they were never replicated.
Right.
So they weren't part of that majority commit point. And the process that happens now is that this primary has to get in sync, the old one has to get in sync with the new replica set, with the new history.
So if this one crashed and came back up online, it now needs to resync to the replica set in order to be a productive node.
That's right. And so in order to do that, what we have to do essentially is to undo this part of the old history, and then we can catch up, we can get the new history and roll forward and catch up that way. But it's not just as simple as chopping off the oplog and getting the new oplog and rolling forward, because we've also made changes in here associated with these operations. And the way that replication has handled that up until recently is to have to refetch the documents that were modified by this part of the history. So it goes off and requests from some node in the replica set copies of those documents, and then it can be sure that any of those changes have been not included in those documents, and it can roll forward the oplog and catch up that way. But that process of refetching documents and also just the code involved in maintaining that path is quite complicated code. And what we realized is that now that the storage layer knows about transactions and knows about timestamps, we can just have it go back to this point. So what we're doing right now is transferring responsibility for part of that rollback process into the storage layer. And what replication can say is it tells the storage layer as it's running what that stable point is, what that majority committed timestamp is. And WiredTiger will make sure that changes more recent than that stable point are not written to disk. So in fact, what we've done is changed regular collections and indexes down here to not use journaling at all in this scenario. So instead, what they do is, as checkpoints are running in WiredTiger, it makes a copy on disk, a point-in-time copy on disk of the collections and indexes at some timestamp. And so there's a consistent point-in-time version of that data on disk that replication can use to roll forward from. So this has a number of benefits. It makes that process of replication rollback more efficient. Mm-hmm. It eliminates some complicated code that we've had to maintain up until now. And as a bonus, which really wasn't our goal, but as a bonus associated with this, we're actually only writing 50% as much data to the journal. So for applications that are high throughput, doing lots of inserts or updates, this should have a significant performance benefit in terms of how much journal data we're writing.
That's great.
Yeah, so I guess to summarize some of what I've talked about, we've made these changes in WiredTiger to support timestamps, which means that the notion of ordering can be supplied to the storage layer from MongoDB from outside. And based on timestamps, we've been able to simplify and improve the way that a whole lot of other parts of the system work, from parts of index maintenance, replication, the way we do rollback here. So there have been a whole lot of knock-on benefits from adding this making these changes right down at the low level inside WiredTiger.
Amazing. What's next?
Well, so once we deliver the transaction project and we have transactions working, we know there are some other areas where we can make further improvements. So one area where we have plans is to improve indexing. And at the moment, you need to choose, when you use MongoDB, whether to do your indexing in the foreground or the background, and there are advantages and disadvantages to going either way. We have this idea that would allow us to kind of combine the best of both worlds there and allow you to build indexes online, but with some of the advantages that you get from foreground index builds today. Okay. So that's definitely on our roadmap. Another area that we're planning to work on is to allow long-running reads as of a point in time. So initially, the design point for transactions is for relatively short-running transactions, but we know that some customers want to be able to start a query at a point in time and query a really large volume of data. Mm-hmm. That's going to involve more kind of low-level work inside the storage engine to make that work and make it efficient, but that's a high sort of priority task for us once we get transactions over the line.
Yes, sounds like a lot of work, but it seems like you're cut out for it. I'm glad we have you. Well, thank you so much, Michael, for walking us through this. I think this is really incredible, and I'm excited for transactions.
Thank you. Thanks, Allie.
Thanks, guys.